Hello, welcome back to Learn Physics. Today's topic we are discussing about the semiconductor electronics. So in last video we did the introduction part, isn't it? Till energy bands we discussed, that is about the conduction band and the valence band. Okay, so conduction band means conduction electrons will be there, in valence band means electrons will be there. They are not ready to go for the conduction if they are not getting any extra energy, isn't it? So all those things we learned, and in conductor, semiconductor and in insulator how the conduction bands will be, that also we learned. Okay, so today we are studying more about the semiconductor. Semiconductor, in which and all ways and how we can make it as a conductor. So in energy band diagram we already learned that in valence band electrons are there, and conduction band and valence band will be having a gap between them which is less than 3 electron volt. Okay, that one we learned. So if this electrons in the valence band is ready to, it can come to conduction band, means the conduction will happen, right? So that thing, how it will be, how we can do that conduction in the case of this semiconductors. So here in the case of conduction of conduction, how conduction is happening in the case of semiconductors. For this, first we are going to study about the intrinsic semiconductors. Intrinsic semiconductor. What is meant by intrinsic semiconductor? Intrinsic, that means it doesn't have any impurity along with it. Okay, so we already learned about silicon and germanium are the semiconductors which we are considering, isn't it? Elemental semiconductors. So if I am considering a silicon or germanium, while I am considering, see, it is an intrinsic semiconductor. Silicon atom alone I am considering, or germanium. So the silicon and germanium has, in outermost shell they have 4 electrons. They have 4 electrons in the outermost shell. So I am considering one germanium. Okay, it has 4 electrons in the outermost shell. So while we are considering a germanium, a group of germanium or germanium substance, while I am considering, it will be having n number of atoms. So see, this is one germanium outermost shell, this is another germanium outermost shell, and here I am considering another germanium outermost shell. Here I am considering another germanium outermost shell. So all are having 4 electrons at the outermost shell. Outermost shell, to get the complete structure, what they should do, they should get 8 electrons, isn't it? So what they will do, it will be in covalent sharing of electrons. Okay, it will be having covalent bonding with the next one. So while they are doing this covalent bonding, so it will be comparing with the, bonding with the next one, and here it will be bonding with the next one, here it will be bonding with the next one, here it will be bonding with the next one, here they will be getting bonded, and here next one, here it is next one, here it is next one, here. If we are giving germanium electrons at this germanium atom at the next side, again it is bonding will be happening. Okay, this is what. So now the structure is complete, right? It is all the atoms will be having outermost shell, 8 electrons will be there. Okay, it is intrinsic, means pure semiconductor. It is not having any other metals along with that. It is pure, completely pure. That means only germanium or only silicon. If I am considering, this will be the structure. Okay, at room temperature this will be the structure. Suppose I am giving temperature, increasing the temperature. So what will happen? This electrons will start vibrating, and due to the vibration, one electron, suppose one electron is coming out. and here a vacancy is there, isn't it? So now this electron is free. This is the free electron, and here a vacancy is developing. That vacancy is called as hole. Okay, so a vacancy is creating and vacancy is called as hole, and the electron is coming out. So the electron which came out, now what will happen? This electron, while they are combining, while the atoms are coming in, it is a substance, a solid substance. So what will happen when the atoms are coming closer to each other? See, this electron may jump to this hole because this hole is having positive charge. Okay, so this electron may jump to this hole, and here the vacancy, this will become electron and this will become a hole. Then next it may come here, and then it will become an electron, and here it will be a hole will be developed. So here electrons also moving and holes also moving, isn't it? So the electron, so this may, chances are there this electron will come and fill the hole. That chance also there, isn't it? While they are colliding each other, anything can happen. When the electrons are moving or the holes are moving, it will be generating a current. So this will happen only at higher temperature than more temperature than room temperature. More than room temperature, if we are applying temperature to the substance, what will happen? It will be increasing its the thermal agitation. Because of that, the electrons will come out from its place and a hole will be created. Hole will be having positive charge. Due to collision, some other electrons can come and overcome this, complete this hole, but the place of the present one will become a hole. So the continuous movement of holes and electrons will happen. This can create an electric current inside that. That is, conductivity is happening because of the movement of holes and electrons. Okay, so here but the number of electrons which is coming out or number of holes which is forming, that will be equal. Number of electrons is equal to number of holes here in the case of intrinsic semiconductors. In the case of intrinsic semiconductor, number of electrons will be equal to the number of holes. That is called as the number of conduction electrons. How much will be the conduction electrons in the intrinsic conductor? It is number of electrons. How many number of electrons? One electron is coming out means one hole will be produced. Two electrons are coming out means two holes will be produced. Okay, this will be equal to the number of intrinsic electrons, number density of intrinsic electrons. Okay, so these are the reasons. So the number of holes produced will be equal to number of electrons. So that is called as number density of intrinsic electrons. Clear? What is an intrinsic semiconductor? In the case of an intrinsic semiconductor means a pure semiconductor, that is either silicon or germanium. Outermost shell is of 4 electrons. This will be in covalent bonding with the nearby germanium atom. When we are increasing the temperature, electrons may come out from its position and a hole will be generated, and the electron which came out will be acting as a free electron. Okay, so due to the collision, this hole will be occupied by some other electrons, and the movement of hole will be happening in such a way. Okay, so that means number of electrons formed will be equal to the number of holes. That is called a number density of intrinsic electrons. Okay, clear? So you understood what is meant by intrinsic semiconductor. Such kind of semiconductors are called as intrinsic semiconductors. Okay. Now, how the current will be moving in the intrinsic semiconductor? Suppose to this conductor, if I am giving an electric field. If I am giving electric field, what will happen? I told you these holes are of positive charges, isn't it? This positive charges, that is holes, will be moving towards the negative potential region, and electrons, that is of negative charge, will be moving towards the positive potential region. Okay, so the electrons also will be moving and holes also will be moving. So what will be the total amount of current which is developed? Current due to electrons plus current due to holes. This is what happening in the case of if we are applying the electric field to it. Okay, so as temperature increases, electrons will be forming and electrons will be developing, holes and electrons will be forming over there, and due to the movement of electrons from where to where, it is randomly moving. Whether it is the electrons are moving randomly, not like that. The holes will be moving towards the negative potential if we are applying an electric field, and if we are applying electrons will be moving towards the positive potential. So the total current developed will be equal to current due to electrons and plus current due to holes. Okay, this is the intrinsic semiconductor, which is a pure semiconductor. Now we are going to study about the extrinsic semiconductors. Extrinsic means if we are adding impurity to the semiconductor. That means impurity means some others. If I am taking a silicon metal, silicon if I am considering, or germanium if I am considering, along with germanium some other element if I am adding, that is called the extrinsic semiconductors. So what is the use of that? That and all we are going to study now. Okay. So next is extrinsic semiconductors. Extrinsic semiconductor means we are adding some impurity to the original semiconductor. Okay, so germanium or silicon we are considering, and along with that we can add some impurity or some other elements if I can add. Okay, so two types of addition is possible. Okay, that is, first one, I can add one pentavalent impurity, or I can add a trivalent impurity. Pentavalent impurity means outermost shell 5 electrons are there. So those elements I can add, or I will be adding trivalent impurity. Trivalent means 3 electrons are there in the outermost shell. So here in germanium or silicon we have 4 electrons in the outermost shell. So along with that 4 electrons, if I am adding a pentavalent impurity, what will happen? See, it is having a 5 electrons at the outermost shell. Okay, but we require only 4 electrons. So it will accept this 4 electrons, and but 1 electron will be extra over there. Okay, so we are getting extra free electrons. Okay, electrons are more in that case. And here in the case of trivalent impurity means how many electrons are there in the outermost shell? 3 electrons will be there in the outermost shell. Okay, so these 3 electrons will be combining with this 4 electrons. It will become 7. Now one more is required, that is no electrons are there to fill that, to complete the bonding. So what will happen? It will be existing as a vacant space, that is holes will be, positive charge will be more over there. But if we are adding a pentavalent impurity, what will happen? This electrons will be more over there. So now we are going to discuss that. Okay, here we are adding impurities like arsenic, antimony, phosphorus. These are the elements which we are adding to germanium or silicon, pentavalent impurities. While we are adding pentavalent impurity, so this is germanium, 1, 2, 3, 4. Along with that, if I am adding a phosphorus, which is 5, 4, 5. What will happen? Here it will join, here it will join with the next phosphorus, here it will join with the next phosphorus, here it will be joining with the, here it will be joining, here, here, here. This thing will happen. But here 1 electron is extra, isn't it? That is 1 negative charge is extra over here, negative. So such type of semiconductor, extrinsic semiconductors are called as N-type semiconductors, or it is pentavalent impurity, if we are adding to a semiconductor, one electron will be extra, one negative charge will be extra. So it is called as N-type semiconductor. Okay, clear? So you understood what is meant by this pentavalent impurity and how it is obtaining. Clear now? So this is extrinsic semiconductor. Externally we are adding some impurity. So we can add two types of impurity, pentavalent or trivalent. Pentavalent means valency is 5. It has arsenic, antimony or phosphorus. 4 electrons, along with 4 electrons it will combine, covalent bonding, but one is extra. So the negative charge, electrons will be more while we are adding pentavalent impurity. So the addition of impurity to the semiconductor, that is called as doping. So what is doping? Addition of impurity to the semiconductor. That process is called as doping, and the two types of doping, that is, first one is pentavalent impurity, that is N, that will give an N-type semiconductor. So electrons will be more over there. Okay, number density of electrons will be very much greater than number density of holes. So at room temperature itself it will be getting more number of electrons, or negative charges will be more. But if we are increasing the temperature, while we are increasing the temperature, the other process also will happen. What is the other process which we explained for intrinsic? Intrinsic means, see, the electrons will come out and holes will be developing. That also will be happening as usual. Okay, and if we are adding the electricity and all, the negative charges will be moving more. That is, IE will be very much greater than IH. Okay, because number of free electrons are more over there. Clear now what is pentavalent impurity and N-type semiconductor? Now, can you explain what is meant by trivalent impurity? 3 electrons. So what will happen? See, the doping is happening with the trivalent impurity. So what are the trivalent impurities which we are adding here? Boron, aluminium, indium. These are the elements, trivalent impurities, which we are adding to the semiconductor. Germanium and silicon, can you try to draw? See, germanium, 1, 2, 3, 4. Here, along with that, if I am adding one boron, what will happen? 3 electrons are there, right? 1, 2, 3. So it will be joining, this will be joining, and this will be joining. Here it will be joining, but for this, it's not having a bonding, isn't it? A hole. It will be existing as a hole over there. Okay, so here, or I can do like, see, this one will be here, a hole will be there. So it is not having an element to, it is not getting a place to overcome its bonding, isn't it? To do its bonding, it is not having an electron. So number of holes, while we are adding this holes, what will, or trivalent impurity, what will happen? Number of holes or positive charges will be more. So number of holes are very much greater than number of electrons in the case of a trivalent impurity. Okay, there the whole current will be more, and then the whole current will be more than the electrons. So in the case of trivalent impurities, this holes will be more, and in the case of pentavalent impurity, electrons are more. Okay, so it is the, so which is more? We will tell usually it is majority. Okay, so here in the case of pentavalent impurity, we will say electrons are the majority carriers. Majority of current carriers are electrons, and holes are the minority carriers. Okay, majority carriers are electrons and holes are the minority carriers. But in the case of trivalent impurity, who is the majority? Holes are the majority carriers and the electrons are the minority carriers. Here, holes are the majority carriers and electrons are the minority carriers. Okay, clear? So the anyway number density of holes is increasing, so the current due to the holes also will be increasing. And here in trivalent impurity we can say Ne into NH is equal to Ni square. Okay, so this will be the Ne is the number density of electrons, NH is the number density of holes, and Ni is the number density of intrinsic charge carriers. So this is clear for you now. Now next we are going to study about how the energy bands in the case of intrinsic and extrinsic semiconductors. Okay. So this is the energy band diagram for intrinsic and extrinsic semiconductors. I will explain you. See, this is the valence band which we draw. This is the conduction band. So the top ones are conduction band, down ones are valence band. We know energy gap is less than 3 electron volt for a semiconductor. Then here in the case at T is equal to 0 Kelvin, what will happen? Room temperature. See, this valence band will be having any number of electrons, but they are not coming to conduction band. One also not coming. In the normal stage it won't be acting as a conductor, so no electrons will be there in the conduction band. But when we are increasing the temperature, what will happen? This will cross and come to, some of the electrons will come to the conduction band. Some of the electrons will come to the conduction band. Okay, so it will be that will be causing number of electrons will be equal to number of holes. Okay, this is what we learned in the case of intrinsic semiconductor. Next we learned about the N-type and P-type semiconductors, that is extrinsic semiconductors. We are doping, externally we are adding impurity. Okay, so while we are adding impurity, what is happening? So if the impurity is not there, here valence band, conduction band, no electrons. Okay, so while we are adding N-type semiconductor, that is N-type, that is pentavalent impurity, while we are adding, number of electrons are, free electrons are more. Free electrons more means it is helping the conductivity. So conduction electrons will be more in the conduction band. And while we are applying the temperature, what will happen? 1 or 2 electrons will jump because of that also. Okay, if we are not applying any temperature also, this will be filled. Okay, holes won't be there, but it will be filled. If we are applying temperature, this number of holes also will be increasing slightly. That is, here holes are the minority carriers and electrons are the majority carriers. And this is the energy band. This is the conduction energy band. It is donor, isn't it? Donating electrons. So donor energy level will be just near to the conduction energy level. So if we are giving slight temperature itself, it can go to this conduction band. Okay, donor energy level, that is donor electrons which are more there, right? So they are called as donors. So donor energy level will be very near to this conduction level. Okay, next is for a P-type semiconductor. What are P-type semiconductors? Number of holes will be more over there, isn't it? So here electrons are less. Okay, so here trivalent impurity we are adding. So while we are increasing the temperature, 1 electron or 2 electrons maximum come to the conduction band. But the holes are remaining in the valence band itself. There it will be trying to move the from one point to another, isn't it? So here this acceptor, it is accepting, it's not giving any electron, so that is called acceptor energy level. Acceptor energy level will be just near to the valence band. So while it is very easy for the electrons to accept the electrons, it can come to this acceptor level and combine with the holes. Okay, clear? So this is what about the energy band diagram in the case of intrinsic and extrinsic semiconductors. Usually when the question asks like energy band diagram, children are having the tendency to draw the same diagram which we learned in the previous lesson, previous video. Okay, so this is about the intrinsic and this is about the extrinsic semiconductors. Here it is 0 Kelvin, that is it is at a greater than 0 Kelvin. This is at a higher temperature. What will be the how the intrinsic and extrinsic semiconductor n-type and p-type it is working. Okay, clear for you? Okay, today's topics are it's easy, I guess, and if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.